Okay, hi guys. So in this video, I'm going to kind of go through the whole factorial between subjects at ANOVA, at least your first example, because that's the one that's the hardest. So you use factorial between subjects at ANOVA when you have nominal IVs, so those are categorical IVs, and you have more than one. And then also when you have DVs that are quantitative. So all ANOVAs have nominal IVs and quantitative DVs. It's just that a factorial between subjects ANOVA is a specific one where you have more than one IV and both or all of your IVs are between subjects. All right, so I want to just review one-way ANOVA real quick because some of you are still, I think, a little shaky on kind of what the F ratio tests. So I'm just going to kind of go through that real quick. So in the module 4, module 4, you worked with a one-way ANOVA, right? So that's sometimes just called a one-way univariate ANOVA. Your book is going to refer to it as that, and it does have a slight or a small section that reviews one-way univariate ANOVA at the beginning, so that can kind of help you a little bit. But you learned about two types of one-way ANOVA, the between subjects, which means you have different people in each group or each category of your IV. And you also learned about a repeated measures one, which is where you have the same people that go through all levels of your IV. So usually you test them at multiple points after they have experienced all levels of your IV. So the example you guys worked with was the diary type, and you looked at whether or not they, the different diaries that they wrote affected their happiness, and every single person experienced all three diary types. So they wrote a gratitude diary and then they assessed their happiness. Then they wrote a venting diary and they assessed their happiness. Then they wrote a regular diary and they assessed their happiness. You didn't have different people in each level of the IV or each category of the IV. So you remember how the t-test was the difference between two means divided by what you could expect that difference to be just due to chance? And things like sampling error, like maybe your sample doesn't really represent the population and that's why you can see effects due to chance. Well, the F ratio kind of works the same way. The F ratio looks at whether or not variance in your DV can be explained by the IV, so that's what's in the numerator, relative to the variance in the DV that is due to chance. So when I say variance in the DV, I mean that you have variability in the scores of your DV, okay? So maybe you're looking at prosocial behavior. Some people will have low levels of prosocial behavior and some people will have high levels of prosocial behavior for that DV, okay? You want to be able to explain with your IV why some are low in prosocial behavior and some are high, right? Okay, so you want to be able to say, well, part of the reason that we have some people that are low in prosocial behavior and some that are high in prosocial behavior is because of maybe what group they were in with regard to the IV. And you want that variance that you're explaining in the DV, the prosocial behavior, you want that to be more explained by the IV, so what video game they played maybe, which was the IV that we worked with in that example. You want that to outweigh the variance in the DV that is just due to chance random factors that you don't really know. So let's look back at that example. Remember, we had different people in one of three groups: a violent video game, a prosocial game, and a neutral game. So that was a between subjects one-way ANOVA because different people were in each group. And we were looking at how those different video games affected prosocial behavior. So how many times they did like nice things, right? And you would have maybe a researcher like observe them and record them. Like how many times did they compliment someone? How many times did they help someone? How many times did they share? So if you look here, prosocial behavior is our actual DV in this example, okay? And then you have the IV, which was what video game they played. Well, look at our prosocial behavior. We have variability in these scores. Some are low, some are high, some are kind of in the middle, right? All right, so there's variability in this DV. We want to be able to explain some of that variability in that DV. We want to be able to explain some of that variance. And we want part of it to be due to the explanation that, oh, yes, it's our IV. It's what group they were in with regard to the IV. So if we look, those that kind of had a low score tended to be in the violent group, okay? Those that kind of had a medium score tended to be in the neutral group. And those that had a high score for prosocial behavior tended to be in the prosocial video game group, okay? So part of the variance in the DV can be explained by what group they were in with regard to the IV. But there's also, there is also unexplainable variance, so unsystematic variance. So this right here, what can be attributed to the IV is systematic variance because it's systematically related to the IV. But there's also chance stuff that's coming in, okay? There's also unexplained variance in our DV that we have no clue where it's coming from. It's just chance factors. That's unsystematic variance, okay? So if our IV was affecting the DV completely and nothing else was affecting our DV, then we would expect all of the scores within the violent video game group to be the exact same because nothing else would be affecting these scores, okay? So we would expect this group's scores to be low, but all the same, okay? Same thing with the neutral group. We would expect everybody in this group maybe to have, you know, the same score, but that's not what's happening. There are other things explaining our DV, things that we can't figure out what they are. So those are the things that are just due to chance, okay? So back to this a little bit. That's what we're doing with the F ratio. You don't see it because SPSS does it behind the scenes and it's literally like 9 equations. It would take you like 15 minutes to even do like one equation probably. But that's what the F test is doing behind the scenes. It's looking at how much variance of the DV can be explained by the IV relative to all the things that are affecting our DV that we don't really know, those chance things. We want this to outweigh this. So we want our F ratio to be larger than 1, okay? If this is larger than this, our F has to be larger than 1, but we want it to be quite a bit larger than 1 in order to say, okay, this definitely outweighs this. Okay, so that's just kind of a review of the F ratio in a nutshell mathematically. So when you get a significant F test, so when the p-value for your F test is significant, it tells you kind of 3 things. At the most basic level, it's telling you that that IV that you're looking at, so type of video game, has a significant impact on your DV, prosocial behavior. It's also telling you what we were just talking about, that systematic variance, that variance in our dependent variable, so prosocial behavior, is attributable to IV, the type of video game, and that outweighs what we can expect by chance. Okay, all the variability in the prosocial behavior are DV that's due to chance factors that we don't know. So the systematic variance outweighs the unsystematic variance. It also lets us know that at least one of these groups from the IV type of video game is different from another group with regard to prosocial behavior. Okay, so we don't really know which one yet. We have to go and look at the post hocs in order to determine that. But it tells us that at least one group is different. So a lot of you might be like, well, why don't we skip ahead to just look at the post hocs, okay? So that was in the previous module. It was several slides in the previous module. But the reason we don't do that is because every single test that we run, every single comparison has a chance of a type 1 error with it, okay? Usually when we want that to be less than 5%. But if we do enough tests, okay, enough comparisons, there's probably a chance that we've committed a type 1 error somewhere, okay? So the F test is kind of like this very, very conservative test that we do first that tells us, okay, there definitely probably is a difference somewhere. And then you kind of go and look at the t-tests, the individual post hoc comparisons to tell where that difference is. So the F test kind of gives us the justification to go ahead and look at those t-tests those post hoc tests. They're actually individual t-tests. It's just they don't show you that in the output of your SPSS. Okay, so in this module, we're going to be working with Factorial ANOVA. All right, so this example that we were just doing, it just has one IV, right? All right, so now we're going to be moving on to factorial between subjects ANOVA, which is where you have more than one independent variable. So this is kind of a basis for a lot of other ANOVAs that you might learn. So when we say factorial, we mean that it has more than one independent variable. So you could, after this particular module, have a good idea of how to do a factorial repeated measures ANOVA, where all of your IVs are repeated measures or within subjects. You could also do a factorial mixed model ANOVA, which is where you have a combination of between subjects IVs and within subjects IVs. Okay, so just an overview of the factorial between subjects ANOVA. Again, factorial means there's more than one IV. It could be a two-way factorial ANOVA, which the two-way would indicate there's two IVs. It could be a three-way, which indicates that there are three IVs. It could even be a four-way, which would be four IVs. You're going to get an F test for every single individual independent variable and all possible interactions between those independent variables. So we'll see that kind of in the example here. So we're first going to look at an example with a significant interaction between our independent variables. So let me explain kind of what that is. So when you have an interaction between your independent variables, it means that your independent variables are interacting, they're working together to produce an effect on your DV. So they're not necessarily working individually on their own, it's their combined effect on the DV that's causing that interaction. So a researcher wonders, this is going to be our example that we're working with, by the way. A researcher wonders how a student's own gender affects their ratings of the course, but also their professor's gender affects the student's ratings of the course. So you're looking at ratings of the course on a scale of 1 to 10, with 1 being very unsatisfied, 10 being very satisfied. Okay, that would make it an interval variable. Usually rating scales are interval variables. And you're trying to determine, well, is that dependent on the student's own gender? Because maybe like females tend to rate professors higher than males. I don't know. This is just a made-up example. But you're also looking at, okay, how does the student's professor's gender affect the student's ratings of their course, okay? So the researcher is not really expecting there to be any differences in how male students rate male versus female professors, but they are expecting there to be a difference for female students. So specifically, he is expecting female students to rate their female professors more favorably than their male professors. So this sentence right here implies that there's kind of an interaction going on, okay? Because it's looking at the combined elements. So when you're female, okay, there will be a difference between how you rate female and male professors, okay? Or rate the course with female and male professors. So our first IV is the gender of the students, which is male versus female. And our second IV is the gender of the professors, male versus female. Both of those are categorical and between subjects, okay? Because we had one student rate one professor, okay? And that professor could be either male or female, and then the student themselves could be either male or female. It was different groups for both IVs. And then their DV is the satisfaction with the course, which is quantitative and interval. So this is a 2 by 2 between subjects ANOVA. So these numbers indicate how many levels of your independent variable are. So it says this would be a 2 by 2 between subjects ANOVA, 2 because there's 2 levels for gender of the student, and then 2 for 2 levels of the gender of the professor. If we had a third independent variable, it might be 2 by 2 by 3, and then that third independent variable might have like 4 levels. So, or that third independent variable might have like 3 levels. So that would be a 2 by 2 by 3. Or we could have a third independent variable with 4 levels or 5 levels, and it would be a 2 by 2 by 4 or a 2 by 2 by 5. So when we run a factorial ANOVA, we're typically going to be describing it using this particular notation, okay? So here's some more examples, a 2 by 2 by 4 ANOVA. So we have 3 independent variables because we have 3 numbers, and each number is indicating how many levels or categories or groups that particular IV has. So 2 by 2 by 4, this would be gender, male or female, employment status, you're either employed or not, and then 4 years of high school, okay? So in our example, we have a 2 by 2, ANOVA, but again, you could have all kinds of different things. But let's get back to our 2 by 2 example, okay? Our gender by professor gender, or student gender by professor gender, I should say. And again, we're looking at how that affects ratings of the course. So when we break this down, we end up with, yes, we have 2 groups that are either rating a male versus female professor, or we have 2 groups that is either male or female for the student, but we really have 4 because we have instances where it's a male student rating a male professor, instances where it's a male student rating a female professor, instances where it's a female student rating a female professor, or a female student rating a male professor. So here's this, gender of the professor, male, female, gender of the student, male, female, okay? So that's kind of why it's called a factorial ANOVA, because when you multiply 2 times 2, you end up with 4 groups, okay? And also, just so you know, factor is another word for independent variable, okay? So if you have, 2 factors, that's 2 independent variables. We have 2 factors here that produce 4 groups. Okay, so there will be 3 different effects that we'll be able to examine in this particular example. We'll be able to examine just the effect that the person's own gender has on their ratings of the course. So maybe overall, females tend to rate professors higher than male professors, regardless of what the gender of the professor is. So this would just be an effect of the student, or the gender of the student. Or maybe overall, regardless of the gender of the student, there's just an effect of the professor's gender. Oops. So maybe overall, female professors tend to get rated higher than male professors, and it doesn't even matter what your gender of the student is, okay? And then we also will look at a variable that's like how these 2 independent variables tend to work together to produce an effect, okay? So main effects, that's the individual effect of a single independent variable. So we would look at the main effect of gender of professor, the main effect of gender of student. Both of those are individual main effects. So we could have a main effect for either of those. So a main effect would be if there were differences between the groups. So a main effect for student gender would be like male students versus female students and how they rate the course, okay? We could have a main effect of the professor's gender on their students' ratings of their course. So that would just mean that overall, regardless of student gender, male professors get rated higher than female professors, or maybe it's the other way, I don't know. Now, interaction effects, that is the effect of one IV on the dependent variable when that depends on the other IV, okay? So let me say that one more time. The effect of one independent variable on the DV depends on the other independent variable, okay? So we are actually kind of expecting an interaction effect in this example because the researcher is saying, basically, the researcher is expecting that the effect of the professor's gender on the course ratings will depend on the student's gender, okay? So what they're saying is the researcher is not expecting there to be any differences in how male students rate male versus female professors, okay? But it is expecting there to be a difference for female participants, okay? So the effect right here, the effect of professor's gender depends on the student's gender. It doesn't matter for males. Males tend to rate male students tend to rate male and female professors the same, okay? But it does matter if you're a female student. So female students will tend to rate female professors higher than male professors, okay? So those two independent variables are interacting, okay? Because the effect, the difference between how males and female professors are rated depends on whether or not you're a male or female student. So it doesn't matter for male students. They rate male and female professors the same. But it does matter for female students. They tend to rate female professors higher than male professors, okay? So that's what we're expecting here is an interaction effect. All right, so your book talks about how when you have a significant interaction, okay, so a significant student gender by professor gender interaction, then you don't interpret main effects, okay? So your book talks about this on page 81, okay? So if you have a student gender by professor gender significant interaction, then you will not be interpreting the individual effects of student gender and professor gender on course ratings, okay? So we'll I'll keep talking about that here in a little bit, but let's kind of look at an example. So the SPSS data file that you're going to want to work with is called course satisfaction, okay? So I have mine open here, I think. All right, so you're going to want to go to Analyze, General Linear Model, Univariate. Okay, I know it's weird because univariate is supposed to be with more than one IV, but in SPSS you can run a Factorial ANOVA. Remember, Factorial means more than one IV. Okay, you can actually run a Factorial IV in the univariate, interface. So our dependent variable, what we're expecting to be affected, is course satisfaction. Okay. And then we are expecting student gender and professor gender to have an effect on course satisfaction. Specifically, we're expecting these two working together, interacting to have an effect on course satisfaction. So we don't expect professor gender on its own to affect course satisfaction or student gender on its own to affect course satisfaction. It's these two working together to affect course satisfaction. So let's put all these over into the fixed factors box, okay? Remember, IV is or factor is another word for IV. So we're going to go to options, and we're going to arrow everything over. This just is telling SPSS that we want to get the post hocs for all these effects, and we also want the means and standard errors for all these effects. We're going to click on compare main effects, okay? Then we're going to click on the Bonferroni post hocs. Those are the post hocs that are kind of the most conservative, meaning you're going to be less likely to commit a type 1 error. You're going to be less likely to say there's differences when you're actually wrong, okay? All right, so we're going to click estimates of effect size and homogeneity tests. This is going to give us that Levene's test, okay? This is going to give us our partial A squared, and we can click on descriptive statistics. Let's click continue. Now, for those of you that are using older versions of newer versions of SPSS, under options, you're going to be able to get these things, but this stuff that we did is going to be under a separate button over here called EM means, okay? So you're going to have to click on options to get this stuff, but to get all of this arrowed over to here, compare main effects and Bonferroni, you're going to have to do that under a separate button that says EM means. Okay, so let's click continue. Now, we normally click OK, but we actually need to click paste, okay? In order to get the post hocs for the interaction, we have to write code for SPSS, okay? SPSS doesn't just give us the post hocs for the interaction. I don't know why, but it never has done that. This has always been something that people have to do. There are entire programs that are all code-based. So that would mean that anything that you did, any kind of statistic that you did, you had to write the code for it. So be glad that we don't have to write the code for everything. My first statistics class was so scary because we were learning all these new statistics, but we were also having to learn how to manually write code in our programs to run the statistics. Anyway, so we're going to click paste. All right. So here's where we have to modify the syntax. So this is our syntax. This is the code that SPSS gets behind the scenes that tells it what to do, basically. We're going to go in and manually modify this code so that we can get the post hocs for the interaction. Because if we end up with a significant interaction, so meaning the professor gender by professor, or professor gender by student gender, independent variable is significant, we need to be able to go and say where those specific groups are different, okay? So what we're going to do is we are going to go here. This is the line we're going to be working with. This is the line we're going to be modifying. So what you need to do is you need to type the word compare in all caps. And you have to do this exactly like I'm doing it, okay? Then you're going to do an open parentheses and you're going to write whatever is the second variable that appears here in this whole interaction term, okay? So the second variable that appears here is professor gender, so we're going to type, you can type it manually or just copy and paste that name. Okay, I left out my R, so I'm going to need to add that. Okay, and this has to be exact. You can't, you know, have like some caps and some not, okay? So we're going to close the parentheses, okay? Then we're going to type ADG in all caps, ADJ, not ADG. Okay, that's telling it that we want to make an adjustment, okay? And we want to do Bonferroni post hocs. Okay, so B, and then you can see it kind of defaults, so you can get Bonferroni. So when you do this for your assignment, guys, this is going to be the same, this is going to be the same, but your variable name, okay, will change out. And again, you need to make it whatever appears second here, okay? So then we're going to space down, all right? And we're going to copy and paste this line. So copy, paste it here. So this line is telling SPSS that we want to examine the interaction. We want to look at the post hocs a particular way. Okay, this is telling SPSS we're going to change this line to tell it, well, we want to look at it another way. Okay, so now we're going to take, so technically this isn't going to make a whole lot of sense yet, but when we get to the end of the example, it will make sense. What we're telling SPSS is that we want to look at the differences in how males and females professors are rated, their courses are rated for each level of student gender for male and female students. So we're going to examine the differences between how male and female professors are rated by female students, but then we're going to look at how male and female professors are rated for male students. This, we're fixing to modify this line so that we can examine the interaction the other way, okay? So we're going to flip this order here. We're going to say professor gender by student gender. Oops. Okay. And then we're going to change this to be student gender. Oops. So what we're telling it now is that we want to look at how males and female students differ in how they rate each type of professor. That sounds like the same thing as what we just did, but it's not, and you'll see here in a little bit that it's not, okay? So right now I'm getting you set up to even run what we are going to be evaluating here in a minute. So let's select all of this, Okay, now guys, this has to be exact. So compare, adjust Bonferroni, adjust Bonferroni. You're going to need to do this for your module assignment. You're going to do exactly what I just did, but obviously your variable names are going to be different. Okay. All right, so let's select all of this and click play. So now we should be able to go and look at our output. Okay. So here is our output. It tells us, okay, how many male students we had, how many female students, how many male professors, how many female professors. This isn't particularly useful. It breaks down the mean for male students when they're when they're rating the courses for male professors. Okay, so the average rating for male students when they're rating male professors is 7.12 on a scale of 1 to 10. And their standard deviation is 0.83. So on average, all the scores in this group were 0.83 points away from this mean for 7.125. Okay, so you could evaluate all of those. This is telling you how many people you had in that group. So you had male, 8 male students rating eight male students rating male professors. Okay, 7 male students rating female professors. Okay. Now we have this Levine's test. So if you have a newer version of SPSS, you'll get a bunch of different Levine's tests, but those you want to make sure you're looking at the Levine's test for the mean, not the trimmed mean or the median or anything like that. So you should be looking for the one that has the same basic result that I have, right? Okay, so I'm going to switch back to my PowerPoint here now, but this output is basically pasted into the PowerPoint, okay? But let me go ahead here. Okay, so our Levine's test is not significant, okay? Anytime you look at significance, that's testing whether there's a significant difference or significant relationship with some other statistics like correlations and stuff. But so remember, the homogeneity of variance assumption says that the variances in scores across these groups, we want those to be the same. So we don't want it to look like this. We don't want one group to have, very little variability and one group to have a whole lot of variability in their scores. They're like all over the place. And then one group to kind of have like medium variability. We want these widths for these different groups. We want the distribution to be roughly the same, okay? So we would want to see a width of about this for every single group, okay? So we do not want this to be significant, okay? It is not significant, so that's good. That means we have met the assumption of homogeneity of variance, okay? So that means it does not look like this. It means that these, okay, are roughly the same, all right? If you have a newer version of SPSS, like I said, you're going to get all kinds of different Levine's tests. You need to look for the one that's just for the mean that basically has this same result that I have, okay? All right, so remember, we're technically testing 3 effects. We get just the effect that students' own gender has on their course ratings. We have just the effect that the professor's gender has on students' course ratings. And we have how these variables are interacting, so the student gender by professor gender interaction, how those variables are interacting together to produce an effect on your dependent variable course ratings. Okay, so your book talks about how if you're significant, if you have an interaction that's significant, which we do, then you're not going to evaluate any of these. And the reason for that is it's basically saying that the effect of one of these independent variables depends on the other, okay? So they're working together to produce an effect on our dependent variable. We can't evaluate how they're individually affecting the dependent variable because it depends on how they're working together, okay? So we do have a significant interaction, so we're basically not going to interpret these. We're going to focus on interpreting our significant interaction. So just as a review, our F ratio is pretty big. It's more than 1, or quite a bit more than 1. So that Systematic variance, that variance that can be explained by our independent variable, which is the student gender by professor gender interaction, outweighs what we can expect by chance, or what chance factors are affecting the dependent variable course ratings, okay? So again, we know this is significant because our p is less than 0.05. We have a very small chance that this effect is a fluke, okay? A very small chance that this effect is not really a real thing out in the population, okay? All right, so we also look at our partial eta squared. This is a fairly large, this is pretty large effect size actually, okay? And this also tells us how much variance this independent variable is accounting for in our dependent variable. So this tells us that 53.6% of the variance in course ratings is due to this variable, the way student gender and professor gender are interacting, okay? So I've just kind of said all that. That's all right down here, all right? Now, so far we know that student gender and professor gender interact to produce a significant effect on course ratings, but that is it. We don't know how that specific, effect kind of plays out. We need to go and look at the post hocs, or they're called the pairwise comparisons in SPSS, to see how that specific interaction is working out. So if you scroll down to the part of your output that says student gender by professor gender, okay, these are the post hocs for that, okay? So before you see you have post hocs just for student gender or post hocs just for professor gender. That's if you want to look at the post hocs for the main effects, okay? Remember, we have a significant interaction, so we're not going to interpret the main effects. But if you did not have a significant interaction, but you had significant main effects, you would be examining just the post hocs for student gender, which would be further up, and just the post hocs for just the professor gender post hocs, okay? But we have a significant interaction, so we need to look at how these are working together. All right, so in this particular way of looking at it, we're looking at the differences between how male and female professors are rated, okay? So this part right here, the more interior part, tells us what is being compared, okay? And then this part tells us for who, okay? So here we're looking at how male and female professors, their courses are rated, that comparison, just for male students, okay? So if we pull over here, we do not have a significant difference, okay? This p-value is not less than 0.05, okay? We have a big chance of a type 1 error here. We have a big chance of saying, if we were to say this is a real effect, we would probably be wrong. There's a 77.8% chance that this difference in these means is due to chance, okay? So there is no difference in how male students are rating male professors versus female professors. And then this right here, this comparison is the same, okay? But if we look here, female students are rating male and female professors differently. So there's a significant difference in how female students rate male professors versus female professors. And we know that because our p-value is less than 0.05. Okay, so let's go up here and look at how this particular interaction or this particular effect works out. So we know that there's a significant difference in how male and female professors are rated by female students, okay? So let's go up here and look. Okay, so it looks like female students are rating male and female professors differently. We know that because of this. But it looks like they do prefer the courses from female professors. And guys, this is just totally made up data. I'm not making any, I don't really know that this actually works out like this, but yeah. Okay, so that's one thing we know. But we could also examine the interaction the other way, okay? So we could look at whether there's a difference in how male students and female students rate male professors, okay? We could also look at how male and female students rate female professors. So that's a slightly different question than what this was, okay? That's the slightly different information from what this was, okay? I know it doesn't seem like it. That takes a little while to kind of think through, but it is, okay? So if we looked at it this way, we would see, okay, male professors are rated differently by male and female students, okay? So we know that because this is significant. We could also see that female professors are rated differently by male and female students. So this is significant also. So that's how we know that. And then we could actually come up here and look at our means. So right here, we were saying that male students don't really rate male and female professors significantly, different. All right, female students do. Here we're asking a slightly different question, okay? So it looks like overall, when we look at male professors, male students kind of rate male professors, better than female students, okay? And then when we look at female professors, male students kind of rate female professors a little bit lower than female students, okay? So that's you're gonna have to kind of think that one through for a little bit, but that one, they are asking slightly different questions, okay? But you typically choose which way you kind of want to look at the interaction, all right? So this is kind of what I'm most interested in, all right? This was what the hypothesis was about. The hypothesis was, basically we said that professors' gender will not matter for male students, which it didn't. And then our hypothesis said that female students will rate female professors better than male professors. There will be a difference here, okay? So this is why I'm kind of focusing on this way, okay? But you can probe the interaction both ways. So here is a write-up. It's in here so you can see it, but guys, I would suggest going to the actual APA write-up that I posted separately because it's easier to see where I'm pulling all the numbers. Here, I don't have enough space to put the output over here and like highlight things, okay? It would just be really, really small, okay? But in that document, here's the APA write-up, okay? And then you have the numbers highlighted, and then you also have those numbers highlighted in the actual output, and you can see what's going on. But basically, we only report the F for the interaction because that was the only one that was significant, okay? And then we break down that interaction with the post hocs. Now, in the next example, okay, you only have main effects and no significant interaction. So in that instance, you would not interpret your interaction, you would just interpret your main effects, and you would also just be writing up the results of the main effects. You wouldn't write up the results of the interaction effect because it's not significant, okay? All right, so I'm going to stop there.